Continue with the program, and I'm happy to introduce now Professor Vivienne, who is going to talk about mapping DNNs to large arrays, including digital processors, SRAM, and memristors. So, Vivienne is Associate Professor of Electrical Engineering and Computer Science at MIT. She got her master's and PhD from MIT. Before joining back as a professor, as an assistant professor, she was a member of the technical staff at the R&D Center of Texas Instruments, where, among other things, she developed algorithms and hardware for the latest video coding standard. And for this, her group, including herself, at TI, received the Emmy Award, something that I didn't know engineers could get here. Her research interests at MIT are on energy-aware signal processing algorithms and low-power circuit and system design for deep learning, computer vision, autonomous navigation, and image and video processing. She has received many awards, and it will be too long to list them all, but just last week she was elected as the awardee this year for the Edgerton Faculty Achievement Award, which is the highest award given at MIT for a junior faculty. Vivienne, thank you very much for joining us today.
Great. Thank you, Jesus, for that nice intro. All right, so today I'm going to talk about deep neural nets, because we're talking about AI in particular, the challenges related to mapping them to large arrays. I'm going to structure the talk in kind of three sections per Jesus' request. So I'm actually going to start out with a bit of more of a tutorial intro to those of you who are not as familiar with neural nets. I'll give a little bit of background in terms of the research that we've done in the past, more on the digital side of things, and then transition into some of the challenges that we see, looking forward for more kind of processing in memory and new devices type of work. So just to start out with, as I mentioned, we're going to mostly focusing on neural nets, primarily just because a lot of the key exciting AI applications today are achieving state-of-the-art accuracy with neural nets, from things like computer vision, speech recognitions, gameplay, and medical applications. In the context of neural nets, what we're going to focus on in today's talk, but this also, a lot of these concepts also extend to other types of neural nets, are actually deep convolutional neural nets, primarily because they're used to process visual data. In our group, we focus a lot on visual data processing. So how these networks work are you have a series of what we call convolutional layers, and I'll explain what that is next. And it allows you to go from low-level features, let's say in an image, which are things like, can you see my pointer? Which are things like edges and so on, and then you can build these up into higher level features as you stack more of these networks together. In modern neural nets, you can actually have many of these layers. We're talking about up to maybe even 1,000, if not more, convolutional layers. And then often, if you're doing something like a classification task, you might follow it by a couple of fully connected layers, and then you get the class of the image itself for an image classification task. So it'll tell you if it's like a dog or a cat and so on in the image. If you're talking about hardware for these applications, what we really care about is where the bottlenecks are. In particular, the convolutions actually account for more than 90% of the computation itself. So it dominates both the runtime and the energy consumption. So if you're going to build custom hardware for anything, you really want to focus on these elements of the neural net. So if we take a deeper look into what we mean by the convolutional layers, or why are these convolutions expensive, it's important to kind of take a closer look. In particular, if you're talking about an image, you start out with a 2D image, let's say. So this would be the input image or a feature map as you're later on or deeper into the network. And you would convolve it with a 2D filter. This is very standard in image processing. So if you've taken, for example, 6344, here at MIT, you would have experienced this. Even 6003 now, we talk about 2D convolutions. A very basic operation. Basically, what you do is you do an element-wise multiplication between the filter and the input image. You get a bunch of partial sums, and you add it together and generate an output pixel. And you would just basically drag this input filter across the image, and that's the convolution. So that's very standard image processing techniques. We've been dealing with this for decades. Nothing special there. What makes it challenging for neural nets is that we increase the dimensionality. So rather than just having a 2D convolution, we extend to the third dimension. So you might also have something what we call number of channels, or the channel dimension. And so then now what you're doing here is you're doing a 2D convolution on each of the channels, and then you have to add the result of all the channels together to generate one output. The number of channels you might have, if you take Alex as example, is between 3 to 192. So you can see this dimension is quite large. Just to give you kind of qualitatively what this could mean is that for an input image, the number of channels typically would be 3 for red, green, and blue components. But of course, as you get deeper into the network, the number of channels will increase. And the reason why the number of channels will increase is because actually what you end up doing is you apply multiple filters to the same input image. So for example, each of these, if we have M input filters, we would generate M output channels. So each of these filters generate one channel. And typically the number of filters that you might have also range in the hundreds as well. So you can see quickly how the dimensionality of this problem is quite large. It becomes much more complicated than traditional image processing. And of course, we know that typically we process more than one image at a given time. We often refer to this as a batch of images. And we can say, let's denote this as n images that you would process at the same time. The key takeaway that you would have from this is that actually we have, for each of these convolutional layers, typically you need hundreds of millions of multiplies and accumulate to do the processing. And you imagine if you have up to possibly 1,000 of these layers. So it's a lot more computation than typical image processing. But there are some important features that are beneficial that we can exploit. So the first thing is that high parallelism is possible. So all of these convolutions actually just involve a bunch of multiplies and accumulate. So high throughput is possible. The challenge is actually delivering the data to the computational engines, to the engine that's doing multiply and accumulate. So just as an example here, if we're doing this MAC, we actually need to take 3 reads and 1 write. So it's a 4-to-1 ratio between memory access and compute. So the data you would read would be the weight information, for example, image pixel information, or you can also think of that as feature map activation information, and then partial sums, and then you would generate the updated partial sum. So it's a 4-to-1 ratio. And in the worst case scenario, if you were to read this data from off chip, which you would actually try to never do, but the energy per access is actually 2 orders of magnitude higher from a DRAM than the actual computation itself. So you're talking about already a 4-to-1 ratio and then orders of magnitude higher in terms of data movement. And we'll see how this is going to be addressed both from the digital perspective as well as a lot of the processing and memory work that can be done to address this. But in general, if you think about a network like, let's say, AlexNet, you're talking about 700 million max, but you're talking about 3 billion DRAM accesses. Again, there are some properties you can leverage, primarily what we call input data reuse, which basically means that a lot of the data that you're using as inputs, so weights and inputs, you can reuse them multiple times for different operations, just in different combinations. Right? So for example, if we're doing the convolutional processing here, there's what we call convolutional reuse, so the pixels and the weights, as I mentioned, same ones will be used, but just in different combinations. When we're applying multiple filters to the same input image, we have what we call image reuse. So every pixel is going to be reused multiple times across filters. And then if you're going to process multiple images in a batch, each weight in the filter is going to be reused multiple times across the different images, so you also have filter reuse. Now, from an architecture standpoint, one of the architectures that we like to look at is a spatial architecture because it lends itself very well to this problem. We'll see that this works for the digital as well as for the more analog or processing memory type of work. So what is the spatial architecture? Basically, it's composed of an array of these processing elements. Each of these processing elements contain some local storage nearby, and the local storage is actually typically very small, under a kilobyte. They also have its own control, and you allow for the processing elements to also talk to each other. And the key goal here is you're trying to basically avoid fetching more data from the expensive memory hierarchy, which then goes to DRAM, which tends to be more expensive. So in particular, if we looked at the breakdown of the energy across this memory hierarchy, if you say, multiply and accumulate as 1x in terms of energy, reading from this very small register file, which is under a kbyte, would be another 1x. Reading from kind of neighboring processing elements would be 2x the energy. Then from the global buffer, it would be 6x the energy. This global buffer is quite a bit larger than register files. We're talking about up to 500 kbytes. And then, of course, if you go to DRAM, like we said at the beginning, that's the worst thing you can do. You're talking about 2 orders of magnitude of energy. So ideally, you'd like to read all of your data from this really small register file here. The challenge, of course, is that we're talking about these very large neural nets with millions of weights and millions of activations, and we're talking about this very small memory here. That's about 1 kilobyte or less. So how do you fit this very large neural net into the small memory? Well, you take this large neural net, you chop it up into smaller pieces, and you try and process it and try and reuse the data as much as possible from this small memory. And the question is, what order of the data should you process to maximize the reuse? So we're not the only ones who have studied this. We know that there's been a huge amount of work in this space. So actually, we went around and kind of classified the different types of approaches people have taken in the past. So one is the weight stationary approach. The idea here is that we want to really reduce the energy cost of reading the weight information for the neural nets. You can store the weights in that register file. And so you don't have to have any weight energy cost, but then you have a lot of pixel and partial sum energy cost. And this is going to be very well aligned with some of the processing and memory approaches that people have taken. Some alternative strategies are the output stationary approach, and the idea here is that, well, for the partial sums, you'd actually do both reads and writes of the partial sum. So maybe you want to hold that locally and stationary within the processing elements. So you really minimize the energy consumption of the partial sums, but now the weights and the pixels all move around. Finally, a third approach is something that we developed within our own group. We're looking at what we call the row stationary approach. And the amount of time I can't get too much into it, but the idea here is that we basically process a row of filters and a row of feature maps within the processing element. So then we can exploit both convolutional reuse of the filter and the feature map within the processing element, as well as maximize the accumulation of the partial sum within the PE itself. So this is called row stationary because the row doesn't move. And of course, we expand this out to the full array size here so that we can do higher dimensional convolutions. Some interesting patterns you might notice here is that the filter information repeats horizontally. So meaning if I read it from the global buffer once, I can reuse it horizontally in the network. Similarly, the input feature map, if I read it once, shown here in blue, I can reuse it diagonally. The key idea, or just the takeaway from the row stationary data flow approach, is that really, while the two other different approaches were focusing on minimizing weight energy or output or partial sum energy, what we're focusing on here is reducing the energy of all the different data types, not just those two individual data types. And what is the overall impact of that? Well, if we compare, this is the weight stationary approach. Shown here, we can see that the weight energy is the lowest in green, and that's by design, but the partial sum and the pixels are large. Output stationary, we actually explored 3 different versions of it. You can see that the red part, the partial sum's smallest, but then the weights and pixels increase. There's another approach, no local reuse, which we don't have time to talk about. And then we have the row stationary approach, which again really tries to balance these 3 data types. And you get about 2x reduction in terms of the energy cost by doing this. So just to also validate this, we actually built a chip called Iris to demonstrate this row stationary data flow. And in general, by leveraging a lot of data reuse, we reduce the number of input or amounts of data access or memory access from the global the global buffer here by 100x, and from off-chip DRAM by over 1,000x. And overall, it gives us an order of magnitude energy reduction compared to a mobile GPU, which at the time of publication, this was back in 2016, was considered state of the art. I should mention that Iris is in 65 nanometer, whereas this GPU is in 28 nanometer. This is joint work with Joel Emmer as well, and if you want any information of this, we have this whole Iris website that you can look up. So this is, in terms of from an architectural standpoint, one way of addressing the energy challenges or data movement of neural nets. But if you take a step back and think from more the application side of things, what people actually care about actually would be kind of the trade-off between energy versus precision. And here we're looking at a object detection task, so we're using average precision as the accuracy measurement. And these, I should just say that this plot was generated based on actually measured data on 2 chips that we developed in our group. These are as much of a controlled experiment as I could do. So these are both 65 nanometer chips. The students started in my group the same time and graduated in my group the same time. So there's the same amount of optimization effort. And what you can see here is that as you go from handcrafted features, which was considered state-of-the-art before neural nets back in 2011 or 12-ish, and we compare it to neural nets, so ALEX and VGG, you can see that certainly neural nets give, or deep neural nets give, 2 to 3x increase in terms of accuracy on this linear scale at the bottom, horizontally. But then if you look at the y-axis in terms of energy, we're talking about 2 to 3 orders of magnitude increase in terms of energy, even when we're talking about custom hardware. Right? So there's still a significant gap that needs to be closed here to balance these things out. And if we really want to have neural nets to be as ubiquitous as something, let's say, like video compression, which we all have on all of our phones, there's still a significant gap. So video compression is typically around 1 nanojoule per pixel. You can ballpark it, and that's on all of our phones. One of the ideal visions is to have neural nets also, neural net processor running on all of our phones with the same energy cost. And right now, you could kind of arguably say that neural nets would, burn your battery, 2 orders of magnitude faster, right? So something to think about in this trade-off always is, if I gave you, an application that can achieve 2x the accuracy, but your battery life would die 300 times faster, is that something you're interested in, right? So we really are interested in trying to bring down this energy consumption here. And so there's been a significant effort of trying to do this, and also the research community. We can see here both on the algorithm and the architecture space, and we spent a lot of time, again, this is with Joel, looking at these different types of approaches people have taken. So if you're interested in this area, I encourage you to take a look at these tutorial papers. We also teach a course here at MIT on this topic. But what we identified by going through all these different papers was we identified several limitations, and I'll just highlight one of the main ones that we found right here. And this is more from the hardware perspective, which is that there's been a lot of work in terms of making neural networks more flexible, but as a result, there's an increased diversity in terms of the number of neural networks that are out there, right? And so as a result, as a hardware designer, since we're focused on hardware here, you need to have a lot more flexibility in your hardware to support all these different approaches. And some of these in particular cause a significant challenge. In particular, the compact network architecture, so they're taking this 3D network and then breaking it down into a bunch of 2D networks where you only have a channel of one. And if you look at existing DNN architectures, the challenge here is that a lot of them often exploit specific properties of the neural network itself. So for example, you will typically see an array of MACs, and if you read one weight memory, you can reuse it multiple times horizontally, and that's good because we want to reduce data movement that was expensive. Similarly, the activation memory, you can reuse it horizontally. But the problem is the amount of reuse and the array utilization is often in these architectures dependent on the number of channels you might have in the neural net, or number of features or batch size. And we know that those evolve for different algorithms, right? And if you have no control as to which ones people are going to run, it's going to be a problem. In particular, if people are trying to run these compact neural nets, so for example, MobileNet, which has become quite popular, they often use these things called what we call depth-wise layers. So as I mentioned, they decompose this 3D filter into 2D filters, and they only have a single channel. And what will happen in your array is only a subset of the array is going to be used to support this, and this becomes a big challenge. And this is also going to be an issue as you scale up the size of the array, right? Because you're not able to fully utilize all the processing elements, and we're going to see this as a challenge that comes up in processing in memory. And it can also be difficult to exploit things like sparsity, which we won't get into. One of the ways to address this is to use a much more flexible data flow. So as it turns out, we were lucky that the stationary data flow is sufficiently flexible to basically try and find reuse in the neural net, regardless of the dimension. So it's not pinning for a specific type of the dimension. Another challenge that you also will face is the network on chip. So how do you deliver data to the array itself in an efficient way? Because you have basically two scenarios. One is that you're processing these very large neural nets that have a lot of data reuse. So if you think back to AlexNet, for example, and so you want to use things like multicast where you read the data once and then use it multiple times. So you basically want a kind of a broadcast or multicast network, which is on the right-hand side of this spectrum of NOx. But on the other hand, you might also want to have the case where you can support these compact networks, and you need to support things like unicast, so that you can keep all of these different processing elements busy, because you don't have that much reuse there. So you need very high bandwidth from the global buffer itself. And so one solution, but it's not an efficient solution, would be an all-to-all network, but that's often too expensive and it's not scalable. And again, we want to be able to scale things up. So one quick solution to this would be, or not solution, I'll be quick in terms of describing this, it would be a hierarchical mesh. So you break it down into two tiers. You keep an all-to-all network at the low level of the NOC itself, right? And then so that doesn't increase with scaling. And then you connect these low-level clusters of all-to-all with the mesh network. And then in general, what you're able to do is you can support all these different levels of delivery that you need to be flexible, high memory bandwidth, high reuse, and grouped multicast, both grouped and interleave multicast. So that was the focus of the second version of Iris, basically to efficiently support a wide range of filter shapes, both large and compact, different layers, depth-wise fully connected convolutional layers. So you can see here some results from MobileNet that cover all these different types of layers. This is the speed up, so you get about a 10x speed up by doing this. You also want to support both dense and non-dense neural networks. This is referring to the weights itself, if it's sparse or not sparse. You also want it to be scalable, so as you increase the number of processing elements, the throughput should also increase. So ideally, the idea is if I build hardware, if I allocate more resources, it should go faster and be more efficient. And so all in all, you get an order of magnitude improvement compared to the first version of Iris. So again, if you're interested in this, we just put this online a few weeks ago. Okay, so that's basically the solutions that people or one example of solutions that people come up with in the digital side of things to address these challenges, particularly the scalability side of things, which is important. Now, if we flip to analog computation, which is more closely tied to things like the new emerging devices that we see, people take a different approach, a slightly different approach. I'll just very briefly show you how analog compute works for neural nets. So again, you're trying to do a multiply and accumulate. What you'll have is you'll have a bunch of these resistors that are proportional. The resistance of these resistors is proportional to or the conductance of these resistors is proportional to the weight itself. You might apply something like a voltage to one side. That could be the input, so your feature map activation. And then based on Ohm's law, you get a bunch of current coming out. So that's the multiply that you get for free. And then with KCL, you add the current together, and that's the addition for free, right? And so in fact, this is what we would call the weight stationary data flow. And there's been a lot of work in this space about using this type of framework to thinking about doing these multiplies and accumulates efficiently. I'll briefly just highlight some of them. So some work is from Mark Baldo, Lou Chalou, and Caroline Ross's group. They're looking at these MTJ devices, these three-terminal devices, and they want to make this device linear for the multiplication itself, but also nonlinear for the nonlinear functions within the neural net. Some other work is from Anantha Chandrakasan's group looking at convolutional SRAM. So how can you change the bit cell of the SRAM itself as well as the peripherals to do the computation of the multiply and accumulate itself. And then, of course, there's many more works, a lot of which are highlighted in today's workshop. So I just want to give you a kind of framework in terms of that's what a lot of these devices can do. You're kind of building in compute at the device itself, and the benefit of this is that you don't have to move the weights at all. So you're really bringing the processing to the memory. And some ongoing work that we've been looking at, this is in collaboration with IBM through the MIT IBM initiative, in the Quest, is looking at what are the challenges when you scale up these arrays. So one of the issues that you face is that when you go in and out of these arrays, often if you're doing analog processing, you need to go from analog to digital, or digital to analog, and then back from analog back to digital. That can be quite significant overhead, so you often want to build these larger arrays so you can amortize the cost of that. But then we might face some of these utilization challenges in scalability that we saw before. So how do we address those? The other issue is how do you address things like non-idealities in the devices and how might they impact the accuracy of your neural net? Can you train your neural nets to be more resilient to those type of things? And then some other work finally that we've been looking at, this is again in collaboration with Joel Emmer, is more from the architectural level. So this is some work also related to DARPA SDH, which is trying to basically see if we can, there's a lot of accelerators being designed for neural nets. They say they're just accelerators in general because of the slowdown of Moore's law. Can we do, quick architectural level energy estimations of these different accelerators that are out there? This is quite different from the past where we would do architectural energy estimation for things like CPUs and GPUs that are much more regular, but now we have accelerators which are much more diverse. So can we build a framework to do that in an efficient way? Primarily things like taking in architectural design description of your design, and you might also use these component level descriptions of your design as well, and these components can be compounded or built together, so you don't have to be too expensive in terms of building these things up, and then you can get a kind of a high-level energy estimate of your system. So why I'm presenting that here is that it might also be relevant if you want to start looking at getting system or architectural level estimates with these new devices that you guys are all designing, right? So you can imagine these component-wise element energy estimators where you can kind of build in energy estimation of just your particular emerging device, and we can stick it into this large framework and get you kind of a system level estimate of the impact of the overall energy system level impact of your particular device. So that's kind of how we could bridge these things together. And then just finally, so we'll have two of my students will be presenting posters today. So Jen Ru will be presenting work on Iris, the algorithms, and the RPU work with IBM. And then Nelly will be presenting some work on Accelergy, which is that energy estimation tool. So if you're interested in that, please go see them, and they can go into more details about that. So with that, I'd like to conclude and welcome any questions. I want to thank all our sponsors.
Thanks, Vivienne. We can take some questions now. Yes.
So you talk primarily about inference and fixed computations. How would you extend this? Because as we learn, we learn new things. We have a creative side of the brain. We also were able to pull up memories, how would you update some of your architectures? Because I'm going to have to add new things that I've learned. I'm not always going to have a fixed training set. Any thoughts or comments on that?
Sure, no problem. So basically, how do you do this for training, if I could summarize? That's the...
Kind of.
Okay, so if you need to change your weights and so on. So I would say for the digital side of things, well, the first thing is you can think of inference as a subset of training, at least in the context of neural nets, right? So a lot of the optimizations that we looked at in terms of reducing data movement for inference side can also apply for the training side of things, with two caveats. One is, so the data movement part is fine, but the other additional challenges that you will often face is, one, you actually have to store the activation values, which you don't have to do during the for pass, and so that's going to increase your memory storage size there. And then the second thing is reduced precision. So there's been a huge amount of work in the community reducing, the bit widths of the various components. Probably with gradients, it's going to be a challenge to go do that as well, although people have been looking at that. So that's on the digital side of things. On the processing and memory side of things, I think that's a great question to ask people who are designing new devices. I think, using it, writing to these memristors and so on, I think people often, you can use it in the inference side. And I think one of the challenges, though, I think people are addressing it here at MIT, is also reducing the writing costs, right? So it's like, can I change the values of those devices? Is that, yeah.
Question?
Yeah.
Just a quick question about the architecture of the ALU. So you have a NOC, right, essentially network on chip, with the ALUs connected to the main
Correct.
SRAM
Yeah.
architecture. I saw a slide there.
Yeah.
What is the read-write time for some architecture like that? And also, do you read-write from ALU to is it a nanosecond range? And also, are you using some sort of a routing algorithm for passing around data between ALUs? Is this part of the design?
Okay, so we've been designing in 65 nanometer low power CMOS. We clock our design up to 250 megahertz. So in the processing element, the ALU, it has both multipliers, there's a pipeline multiplier, and some SRAMs in it. We use standard SRAM, so everything is very standard, right? This is all standard CMOS, like the digital library you get from ARM and TSMC, right? And the NOC, we designed it so that you don't have any, at least in the sizes that we explored, you don't have any additional delay issues. Of course, as you're growing to much larger delays, then you can imagine the transport time on the NOC will also be an issue, and you can imagine just piping that. People have done that before.
More questions? So Vivienne, this framework that you have designed to evaluate the energy efficiency of
the Accelergy that Nelly's
future
done.
systems
Yeah.
allows you to estimate how far CMOS will be able to go, if you have a sense of the characteristics of the future nodes. And that should be the floor beyond which analog technology will have to
Correct.
go. And so do we have a sense of what that floor is?
So I should say this is ongoing work. But what we're hoping, right now we're building up this framework. This is more for DARPA SDH, but we're building up this framework for digital components and trying to validate the accuracy on various digital components. But with this framework, you could imagine swapping out the libraries and putting in more advanced process or advanced emerging devices in, and then you can at least get like a system level view of the energy. And so it depends on how we build those particular energy estimation components for these emerging devices. But you can actually see in the context of all these other aspects, like the peripheral logic and so on, what is the impact of these particular devices. Does that address your...
Yeah, but I'm concerned about how far CMOS is going to go, and what does it mean in terms of the sort of the limit of energy efficiency of conventional CMOS technology.
So I would say that determining how far CMOS, I would leave those to the device folks to be more expertise. The goal here is to provide a framework so that you can at least, once you have a reasonable estimate, you can plug it in and get a system level estimate of the overall impact of your particular device, whether it be CMOS or not CMOS, on the overall system itself, as opposed to...
One more question.
For this tool, the comparison makes only sense if you keep the classification accuracy constant, right?
Correct. Well, okay,
So how do you build this in this tool?
Correct. So this is a tool. We don't actually deal with, so you can choose what kind of workload you want to run on it. It's just a way to model basically the energy consumption. And so if you, so from a use case point of view, I certainly agree, I don't have time to talk about that, but we should certainly consider things like accuracy is really important. You shouldn't compare something that's very low accuracy with something high accuracy. But assuming that people are comparing fair things. This is at least a mechanism that they can go about comparing it, like measuring or estimating what the energy consumption is. The inputs to this tool depend on the user, and so it depends on how they want to use it.
All right, we need to move on. Thank you, Vivienne,
Yeah,
for a great
thank you.
talk.